Rates of reaction worksheet higher. Question 1. Which of the following changes would not cause the rate of a chemical reaction to increase? So if we increase the concentration it will, if we heat it it will, if we grind it to increase the surface area it will, but using a larger volume of solution but keeping the concentration the same is the same as diluting it, so that's not going to increase the rate. So 1.2, what is the name given to the minimum amount of energy which particles must have if they're to react when they collide? This is the activation energy, and remember that on the energy diagrams as the hump between the two energy levels. And 1.3, explain why adding a catalyst to the reaction mixture without changing any other condition can cause the rate of the reaction to increase. It's simply, it lowers the activation energy, so it makes it that the particles don't need so much energy in order to react. Okay, so this time we're just matching up letters to these statements. So which one produced the most product? Well, the biggest change in mass loss was achieved by C. Which one finished first? Well, B went flat first. And which one had the started at the slowest rate? If we look at the gradient, the more gentle slope is for A. Question 3. On the same axis as this graph here, sketch a curve to show how the volume of hydrogen produced would change over time if an identical piece of magnesium was added to excess hydrochloric acid with a higher concentration. Well, if it's a higher concentration, it's going to be a steeper curve, so I've tried to draw a steeper curve here, but you're going to get the same volume produced, so it's going to flatten off and reach the same level there. Now state two properties of the collisions between particles that affect the rate of a reaction. It's the frequency of collisions, how often they collide, and also the energy of the particles. They're the two properties. 3.3. Use the collision theory to explain why increasing the concentration of a reaction increases the rate of reaction. Well, it's 2 marks here. The first one, there will be more particles crammed into the same volume, so there will be more collisions per second. If they're all squeezed into the same volume, there's going to be more of them banging into each other. How would you expect the rate of reaction to change if the magnesium is cut into smaller pieces? Well, doing that, we're going to increase the surface area, so the rate would increase. Explain why cutting the magnesium into smaller pieces would affect the reaction like this. Well, smaller pieces equals the bigger surface area, that's the first mark, and the bigger surface area equals more particles are available to collide. And then lastly on this one, state one change that could be made to change the rate of reaction other than changing the concentration or size of the pieces. Just change the temperature. If you increase it, it'll go faster. Okay, so question 4, which is the grade 7 to 9 question, now asks, explain using collision theory whether or not these changes will increase the rate of reaction. So here are the changes, increasing the volume and increasing the temperature at which the reaction is carried out. Well, it's 5 marks, so the first mark is increasing the volume means particles are more spread out, so there'll be fewer collisions, which is marks 1 and 2. So that's not going to affect it at all, so this would slow the reaction in fact. Mark 4, increasing the temperature, now that will give the particles more energy, so they'll collide more often and with more energy. So Mark 5 says this will increase the rate of reaction. And 4.2 with cerium oxide is when cerium oxide is mixed with hydrogen and iodine gas, the rate of reaction increases. What does this suggest about cerium oxide? Simply, it's a catalyst. State whether the reaction equation will change if cerium oxide is present in the reaction vessel. Well, in the last question we said that it was a catalyst, so no, the equation won't change, and that's because the equation stays the same as a catalyst is not used up in the reaction. It makes it go faster, but it's not part of the equation. Now, sketch and label 2 reaction profiles, one with a catalyst and one without a catalyst. So we know that we've got more energy in the reactants, it says so in the question, than we have in the product. So these are the 2 lines here. But then if we have a catalyst, we have a lower activation energy for our energy profile, excuse the diagram, but if we don't have a catalyst, we have a much higher activation energy.